Yes, as you said, I work for the Institute of Nanoscience and Materials of Aragon, and also for the Norwegian University of Science and Technology of Norway. And in this talk, I would like to present some of our ongoing research on the implementation of natural feedstock, that is diatom silica, on working anode for lithium-ion batteries. So lithium-ion batteries, as you might all know, this is like the governing technology for portable electronic devices, but also due to their potential to contribute to zero-emission mobility and the storage of renewable energy, they are going to play a much more preponderant role in the future as a technological pathway to climate change mitigation, energy security, and also energy sustainability. So in this matter, the kind of raw materials that we use to make the batteries is becoming more and more a strategical asset at the global level, right? Because we need to use materials that have a low carbon footprint to meet this climate neutral economy, and also to be sustainable. That means that we need to make sure that we don't have supply risks in the future, for example, of the raw materials of the batteries. So the basic working principle of a battery, we have a positive electrode that is called the cathode, a negative electrode that is called the anode, and an electrolyte that is in between the cathode and the anode. And then when the battery is charging up, the positive electrode will give up some of its lithium ions, which will move through the electrolyte to the negative electrode. And then when the battery is discharging, the lithium ions will move back across the electrolyte to the positive electrode. And in this way, it will produce the energy that powers the battery. In both cases, the electrons will flow in the opposite direction to the ions around an outer circuit. So in the case of the positive electrode, they are normally made of lithium cobalt oxide, and in the last years, we have more and more lithium iron phosphate cathodes. But apart from lithium, there is one material that is a fundamental part of all lithium-ion batteries, regardless of the cathode chemistry, and that is graphite. So graphite is the major component of it's the major component of lithium-ion battery anodes, and by weight is the largest constituent. So graphite anodes have a storage capacity of 372 milliamps per grams, which worked well in the past, but is not enough for next generation lithium-ion batteries. But the good thing about graphite is that it's quite stable. And this is because during the charge and discharge, the 2D host structure of graphite, as you can see in the picture, will move to allow the insertion of lithium ions between these layers. And in the discharge, this space between the layers will change a bit. But the change is not so big, so there is not much structural damage to the host structure during charge and discharge, and that's why they are very reliable material, graphite, silica anodes. But if we start, so on one hand, we have this problem of the limited storage capacity. But on the other hand, we have the problem of how the graphite is made of, what is the source of graphite. So in case of commercial graphite, it can be produced either from natural graphite or synthetic graphite. So natural graphite is obtained by crushing and then roasting a mined product, which is graphite. But to get the purification grade that we need for battery grade anodes in lithium-ion batteries, this natural graphite has to undergo a lot of purification steps, which needs a large amount of HF and also sodium hydroxide, which are harmful to the humans and also to the environment. In the case of synthetic graphite, it is made by using a byproduct of oil refining, which means that we are burning off hydrocarbon feedstocks and therefore releasing CO2 gases, NOx and SOx, and also particulate matter. So in this case, we are quite in a problem with this using graphite as the raw material for lithium-ion batteries. So just to show you some like a more applied thing, I would say, here is like a representation of an electric vehicle, and the amount of graphite that an electric vehicle uses nowadays is about more than 50, I would say 50 kilos of graphite. And today we have 10 million, approximately 10 million EVs on the road, but it is expected that for the year 2014, we will have up to 900 million of EVs. And that will consume a lot of graphite. And this is only mentioning the transportation sector, but also the lithium-ion batteries will be used in other market options. So this means that we have to really think some alternative material to graphite in order to power next generation lithium-ion batteries. So one alternative to graphite is silicon. So silicon has a theoretical storage capacity that is about 10 times higher than graphite, which is really impressive. This is theoretically. Has also low working potential, which is what we want to have for the anode material, but has the problem of a low stability. And this is because during the lithiation and delithiation of silicon, there we have an occurrence, a repetition of expansion and shrinkage of the particles. And this causes irreversible structural changes, crack formation, and leads to particle pulverization at the end. And this causes really poor cycling stability of the anode and also loss of electrical contacts between the components. And therefore, the cycle life of silicon anodes is really short, and this is the major drawback that is really hindering the commercialization of pure silicon anodes. Regarding how this silicon is produced, normally one of the industrial ways to produce silicon is by mixing coke or coal and quartz, and then making really high temperature treatments. And also this again gives emissions of CO2, NOx, and solids and sulfur oxide. So I would say that there are many things to improve in the production of silicon in order to get to have really low carbon footprint on its production, but also there are many things to improve on the engineering on the silicon to get rid of these stability issues, I would say. So another alternative to graphite is silica. So silica has been proposed quite recently as anode material because, as you might know, silica is an insulator, so normally it's not the first option when we think to use silica for a battery. But some studies have shown that silica works quite well. It has a theoretical capacity that is very close to the one of silicon and still much, much higher than the one that graphite has, and has much higher stability than silicon. And this is really interesting, and that's why this is a nice option to explore as anode candidates. So why does silica has this nice stability? So there are not much experimental results on this, but there are some theoretical calculations in which it is thought that the silica reacts with lithium as a in situ convertible oxide, which means that silica will create silicon upon lithiation plus other components. For example, lithium silicate, lithium disilicate, lithium oxide, and so on. And the produced silicon will further react with lithium with a known reaction, and then all the rest of the phases, the silicon oxides and the lithium oxide will serve as buffer phases to the silicon expansion and shrinkage thing. So at the end, we will have some silicon that will be lithiated and delithiated, but on a matrix of non-active species. And this will confer to this silica anode high stability, but also high capacity. So when we look into which are the natural silica sources, silica the good thing is that we don't need to produce it because it's already in nature and it's one of the major constituents of the Earth's crust. So we have full lot of availability of these resources. We can easily find it in sand or clay, even in rocks. And also there are some biomaterials that have silica, and I will mention one of them in this talk, and is diatoms. So diatoms are a kind of algae, it's a microalgae actually, that is present in every ocean, sea, river, lakes, and even in soils. So they are really high efficient in photosynthetic systems. They have even higher CO2 uptake rates than forests. And they produce 20% of the planetary oxygen. So I would say that these diatoms play a really important role in our planet. And what is really nice about them is that they synthesize these nanostructured silica shells through biomineralization processes. So this, for us, we think this is a really nice way to get some nanostructured silica for lithium-ion batteries. And there are two ways on how to get this algae. Either we can harvest it from the ocean, or we can cultivate it. So nowadays, these algae are cultivated. There are many companies in Norway, in Sweden, in the US as well, that are cultivating this algae to do some fish feeding. But until now, that was the only application that they found for them. So in our case, we contacted a company from Norway that they do harvesting of algae, and we asked for a bit some algae just to test it on the lab and to try to implement this natural feedstock on a working anode. So as you can see in this slide, this is the extrusive algae. If you see, we have like a bottle of water from the ocean, and the diatoms are dispersed in this solution. And then we have to repeat many sequences of washing and wet sieving to get rid of all the salts and stuff that are coming within the water of the ocean. And then we do some calcination to get rid of some organic components that the algae have. So the goal is to only have this inorganic part, that are the silica shells of the algae. So what you can see in the lower part of this slide is how the algae really looks like after the calcination process. You can see the algae you can see like they're like a huge discs of some tens of microns, but normally during the sieving we break them a bit, so you can see that we have some flakes of these diatoms. And looking with the same, you can see this really nice nanostructure that they present. And you see different nanostructures because these algae are composed by layers of silica walls, and each layer has some nanometer thickness. So this is like really something we wanted to look into. And on the right side of the slide, you can see some 10 EDX mapping of these diatoms, and you can see that the major component is silicon together with oxygen, and we have some trace amounts of potassium, calcium, and magnesium as well that are incorporated through this biomineralization process together with the silicon. So what we try to do is to we adapted some experimental procedures to use this material on an anode. So what you can see here is the first thing we wanted to do is to reduce the particle size of the diatoms. For this, we implemented some ball milling procedures that are not quite easy because these algae, the silica shells are quite hard. So at the beginning, where the algae were really building the balls because they were harder than steel. So we had to adapt a bit and use some other balls from tungsten carbide, and then we successfully ball milled the algae. So we moved from in particle size from an average size of 17 microns to about 470 nanometer particles. And as you can see, the shape of these particles are not spherical, but they are rather irregular. And after the milling, what you can see on the graph, that is the T-plot area, the external surface of the area of the algae increased quite a lot after the milling, but the micropore remained the same, which is what we expect. Right? With the milling, we just increase the surface area that is exposed. So after the milling, we also need to do some coating of the particles with some conductive material. And this is because we don't want to have the silica particles in direct contact with electrolyte, because that will damage the particles. So we need some protective layer to prevent this direct contact with electrolyte, and also to add some conductive character to the particles, so that we can decrease the internal resistance of the whole anode. So for this, we implemented some carbon-coated treatment. So we play a bit with a lot of parameters. We use different carbon precursors, different temperatures, different percentage of carbon precursor to see which was the optimized way of doing the coating on the particles. And we ended up using sucrose as a carbon precursor. And after some mixing and drying of this mixture of sucrose and silica, we got a really nice coating of the silica particles. So now we have a composite that is made of silica and carbon. And what you can see in the lower figure of this slide is that according to TGA results, the amount of carbon in the resulting composite is about 13%. And also you can see from 10 micrographs that the thickness of this layer that's covering the outer surface of the particle is between 16 and almost 60 nanometers. And you can also see that this carbon is also in the pores, in the pores of the silica. So which means that it's really covering everything. So the next step after this was to make a battery, a half cell, I would say. So for this we made a slurry, and for the slurry we mixed 75% of this active material, that is the silica composite, and then we added some carbon black that serves as a conductive additive and helps to the conductance of the ions within the electrode, and then some binder, that was a sodium alginate binder that would help to connect all the components of the electrode. And then we casted this slurry on top of a copper foil using the Dr. Blade method, and then we assembled the electrode, and we punched out the disk of electrode, and then we assembled it in coin cell using some standard electrolyte, that is LiPF6, and we made some coin cells to do the electrochemical tests. So the first results we got using this new material that comes from a natural feedstock are in this slide. So as you can see on the left, we had to perform some activation cycles at the beginning, because we were seeing that upon cycling, for each cycle, each electrochemical cycle, we got like a higher capacity each time. So we made very slow charge and discharge cycles to see what was the maximum capacity that we can get from this material. And after 5 cycles, we reached the stable capacity. So we call these activation cycles, and then once we reach this capacity, we speed up a bit the cycling, so by increasing the current rate, and then we perform 100 cycles of charge and discharge to see how the material responded. So in the upper figures, you will see the profiles of the charge-discharge experiments, galvanostatic cycling, and on the lower part you can see the differential capacity plots. And what is very interesting from these differential capacity plots that one of them corresponds to the activation stage and the other corresponds to the galvanostatic cycling stage, you can see the emergence of some peaks. And those peaks are related to silicon lithiation and dilithiation, which means that this is really happening, that the silica is converted to silicon, and this silicon starts to react in this matrix of inactive species. So on the right part of the slide, you can see a comparison of the coated versus uncoated diatoms. You can see the green dots represents the uncoated milled diatoms, and you can see that the specific capacity is not quite stable. It increases a bit and then it lowers. Where in the case of the coated diatoms, you can see that the capacity is really stable, which means that the coating was very effective. But in addition to this, if you see the differences between the coated and the uncoated on the lower part of the figure, you will see that when we make these capacity rate tests, that means that we are changing the current and cycling the anode faster and faster each time. When the material is coated, the capacity is much higher than the material is uncoated. So this means that, again, that it's necessary to do the coating, and in this case, it was quite good. So one of the most important results of this part is that we were able to reach the capacity of 850 milliamp per gram after 100 cycles of charge and discharge, and the capacity was quite stable after this charge. So I think this is one of the results. Also, we did some inspections to the cross-section of the electrodes to see how the morphology of the anodes evolves upon cycling. So what you can see in the left part of the figure is the cross-section of the pristine electrode, then the electrode after the electrochemical activation, and then the electrode after 50 cycles of galvanostatic cycling. What you can see from the figure is that the thickness of the electrode increases with cycling, which means that we do have this expansion of silicon after all. And on the right hand, you have a top view of the anodes, and you can see also that after activation and after the galvanostatic cycling, we start to see some cracking of the surface of the electrode, which also means that there is some issue with the volume expansion of silicon that is little by little affecting the morphology of the electrode. Even we are not able to see this in the electrochemical data because it looks quite stable. This means that on the long run, if we make more cycles, we will have the effect of losing some power because of these volume changes of the silica. So one strategy that we're trying to do now is to try to use this silica into graphite electrodes and to try to buffer more these volume changes and to see by Eclipse if this is really occurring or not. But I would say yes. Now these are our preliminary results on the use of this algae. So as a summary, I can say that we established an experimental procedure to implement this natural feedstock into working negative electrodes for lithium-ion batteries, and we were able to reach a storage capacity of 850 milliamp per grams after 100 cycles, which is much higher than the one that is displayed by graphite, that is about 372 milliamps per gram. So this is on to now. So I thank you for your attention and also for the funding of this work.
Thank you for nice talk. It doesn't work. No. Okay. So thank you. You talked about usual when you talked about silica. You showed usual sand and rocks. Did you try to use them as anodes?
No, because we would like to do is because I would say that the aim of our work is to be able to cultivate our nanostructure silica. Because later on, if we succeed on this, then you can engineer a bit how this, and by changing the cultivation media of the algae, you can change a bit the morphology and the nanostructure. So this is the direction we wanted to take. So so far, what I know is with the sand, you don't have this internal nanostructure or even with clay. So yeah, we wanted to try with algae because we see that if we make it work, then we can play a lot with the nanostructure and so on.
I have next question, another question. It's well known that 100 cycles is not enough for modern batteries. Did you try to cycle and more than 100 cycles?
That's what we are doing right now. I mean, up to 200 cycles, it's quite stable, and then after 200 cycles, we are observing a bit of the decay on the capacity, but not so much until now. But we haven't performed like a higher cycling.
It's interesting. And maybe last question, if it's possible. You talked about uncoated silica anodes. So what does it mean? Did you use carbon conductive powder or didn't use it at all?
Yes, we used. So we wanted to use some, I would say, cheap and also I would say eco-friendly supplies. And that's why we use sucrose as a carbon precursor to make the coating. But yes, I would say we have 13% of carbon in the total composite. But the coating is something that is, even graphite anodes have some coating. So it's normal to any anode material to have some coating layer. So it's something that, in any anode you will have.
You also thought that silicon oxide, you tried to protect silicon oxide from electrolyte. I thought it's quite neutral for this kind of solutions, liquids.
Well, yes, well, but it's not. I mean, when you have an electrolyte and you reduce, I mean, you are trying to, when you are changing the potential, you will have some reduction products of the electrolyte that will form some, what is named the STI layer, that is the solid electrolyte interface, and we need to have a lot of control on this interface. And it's very important not to have the material in direct contact with electrolyte because then it will be more affected by it. But you have some, some problems. Not,
Thank you very much.
Okay, thank you very much. Ms. Blanco, I have one quick question. So what happens instead of, let's say, coating silicon dioxide, you coat the silicon? And then, so could it be also a little bit more stable because it will be kind of encapsulated with the carbon in the shell? Then it would maybe just reduce the cracking and this would give you maybe better.
So that's, I mean, one of the strategies to improve the silicon because is to, first of all, to do some nanostructure in a bit, and also to have this carbon layer that will buffer a bit. But the difference on the volumes is more than 300%. So you cannot solve it just with this.
Okay, so thin layer.
Yes, so this commercially, I know that, for example, Panasonic, they are using some SiOX compounds. So it's not either silica or silicon, but some intermediate compounds. And they are mixing it with graphite. So they have, in total, I would say, up to 8% of this silicon-based material on the graphite structure. And still, you have problems with the volume expansion. Yes, so it's quite, it's a problem, really,
Okay, so then thank you very much again.